Hopefully yesterday each of you were able to get a chance to look through the spectrometer, and hopefully you were able to look both at the light that just comes through the windows and each type of gas in the tube when it's lit up. And when you look through the spectrometer at the light that comes in through the windows, you should have seen something like this top line right here. Okay, you see all the colors of the rainbow just kind of spread out, going from red to blue. Or maybe in that one it goes from blue to red, left to right. I don't remember. And if you were able to line it up correctly with the tube, when you look through the spectrometer for the gases, you should have seen something like this second line, where you see specific lines inside there. Now the blue ones tend to be hard to see, but you should have at least seen a red line and maybe a green line and maybe at least one blue line. At least for the hydrogen. When you look through for the argon, you should have seen lots of other lines. Okay, this is what we call an emission spectra. This kind of pattern is what you get when you separate that light that was given off when we send electricity through those tubes. So even though we saw kind of a purplish light through the hydrogen, when we separate that light, we get these different colors. We get these specific lines in that spectrometer. And those specific lines correspond to specific wavelengths. So even though it looks kind of purplish coming out, it's really just a few different wavelengths of light mixed together. We call it an emission spectra because it's emitting, it's actually giving that light off. What's interesting is if we took a white light that gives off the spectrum like we have up here at the top, and we took it and shined it through that hydrogen, what we would see is that those actual bars, instead of showing up like when we make the glass glow, we would see them missing. And this is what's called an absorbance spectra. So an absorbance spectra would show the same pattern, but those lines would actually be missing instead of showing up. And what's interesting is that certain elements, and you saw that the difference between the argon and the hydrogen, certain elements will give certain wavelengths of light off if you get them glowing, but they'll absorb those exact wavelengths as well if light passes through them. And this is actually how we tell what elements are in stars. We take spectrometers, better ones than, of course, the one that we have back there, and we look at starlight, and we look at the light from the sun, and we're able to see places where holes, basically wavelengths that are missing, and we know that those elements are there inside the sun. So this gives us a pretty cool way to actually fingerprint stars, basically get a fingerprint of different elements. And even now, with the better telescopes that we have, we're able to take light that comes from stars and passes through the atmospheres of the planets that go around them and see which of those lines are missing, and we're able to tell, oh, this planet actually has carbon dioxide in it. This planet has methane. This planet has oxygen. So we can actually tell what elements are in those planets even though they're hundreds of light years away. So this shows the specific hydrogen lines, and here, yeah, this is the way it is actually in the spectrometer. We've got a red line, we've got kind of a light blue line, maybe green, depending on how you want to describe it, and then you probably didn't see these very well, but you actually do get a darker blue line and a light purple line and a very dark purple line, although those tend to be fairly faint. And these are all in the visible light, and this is the emission spectrum for hydrogen. It's called specifically the Balmer series because, some dude named Balmer, of course, discovered it. So the Balmer series shows the specific fingerprint of visible light for hydrogen. And again, you have the same absorbance spectrum if you shine the light through it. But we're going to stick with the emission spectrums and look at that and what that tells us about the atoms that are interacting and giving off this light. Okay, just to kind of show you and compare, I guess we don't have argon up here, but of course argon had lots of lines. But you can see each different element, hydrogen, sodium, helium, is going to give specific different lines, and we can use those to tell those things apart. Not only that, we could actually take a mixture of, say, hydrogen and neon, And because those lines, not all the lines are going to occur at the exact same places, we could have a mixture of those, and based on how bright the lines are, we can actually get a handle on, okay, it's 75% hydrogen and 25% neon. So it gives us an accurate way to not only tell what elements are in a gas or are in a star, but what percentages are there as well. Okay, now what does this have to do with atoms and electrons? Well, light is produced when electrons fall from higher energy levels to lower ones. Oops, let me fix my spelling. Can't even spell right when I'm typing. So let's think about a hydrogen atom. It's got a single electron, okay? One electron, that's it. And that electron we know is going to be in that first energy level. We could, if we did the electron configuration, it would just be 1s1. It's like the simplest thing there is. When the right amount of energy interacts with that electron, it can shoot it up to a higher energy level. So it doesn't necessarily have to stay in that first energy level. It can actually move around. And that's what we did when we sent the electricity through that tube of hydrogen. We electrified it, and that energy, the electrical energy, kicked those electrons in the hydrogen up to higher energy levels. The thing is, those electrons don't want to be in the higher energy levels. I mean, we've learned that with the electron configurations, they always fill from the lower energy levels up. So as soon as they kind of get kicked up, they're going to fall back down. And when they fall back down, they're going to give off light. Now, the type of light that they give off is going to be dependent on what energy levels it's moving between. So here, if you take a look at this, we can see this red line right here is going to correspond to an electron that comes from the third energy level and falls down to the second energy level. So when it makes that transition and it goes from 3 to 2, red light is going to be produced, and there's going to be a bunch of atoms that have those transitions from 3 to 2, so you're going to get this line of red. Over here, this light blue is going to correspond from an electron moving from the fourth energy level down to the second one. Because that is a bigger jump, that corresponds to a higher energy photon, a higher energy light wave. So it's going to be more blue, because we know that more blue light, the bluer it is, the higher the frequency, the more energy it's got. Okay, if we go over here to the darker blue, that's going to be a 5 to 2 energy jump. And we could fill out for the purple 2, even though they didn't put it on this diagram, that would probably be a 6 to 2 energy jump. So we get multiple lines because there's all sorts of atoms that are going to be doing different things. Some atoms are going to have electrons that are coming down from 3 to 2. Some atoms are going to have electrons that are coming down from 4 to 2, and some are going to have electrons that are coming down from 5 to 2, and so on and so forth. If you just had a single atom, then it would only, and it did it once, it would only give off one color of light. But because we have these mixtures of atoms and they're all doing different things, that's why we get the different lines. So even though hydrogen only has one electron, it doesn't have to just make one energy transition. It can jump, any one of these different combinations. Now you may notice these all correspond, these visible light ones all correspond from electrons jumping down to the second energy level. But that electron's not going to stay there. It wants to be on the first energy level. So it's going to jump, after it makes that jump, either from 4 to 2 or 3 to 2 or whatever, it's also going to jump again down to the second energy level. And that's going to give off light as well. But that light is going to be a higher energy. And so it's going to be given off in the UV spectrum where we can't see it. So this here kind of shows the energy level jumps. And what we've been focusing on is what's called, again, the Balmer series. So the Balmer series is going to be visible light. Okay, the visible light is given off when electrons make transitions from some higher energy level down to the second energy level. And each one of those jumps is going to give off a different color of light. For that electron to jump back down to the first energy level where it actually wants to be, as we can see here, that's a bigger energy gap. There's more energy that's going to be there, and this is going to actually correspond to ultraviolet light. So that gas that you guys had in that tube and that was giving off light, it was giving off visible light that we could see, and we could see through the spectrometer, but it's also giving off UV light because those electrons are also going to be, and you know, every electron that gives off visible light has to fall all the way back down to the first energy level, and it's going to give off some UV. But there's also electrons that are falling all the way from 6 to 1 and all the way from 5 to 1. Any one of these combinations is going to give you a certain type of light. Okay, up here above visible light, if we have energy transitions from any energy level down to the third level, that's going to be given off in infrared. That's lower energy because it's a smaller gap between energy levels. So as you go up, you get smaller and smaller gaps in energy levels, and there's not as much of energy in those transitions. So the biggest transitions have to do with going all the way back down to that first energy level. Okay, now the thing to keep in mind is this is just for hydrogen. All this stuff, as far as whether it be visible light or not, would change if we were looking at a different element. And so that's why argon, one of the reasons why argon has so many other lines in it. The other reason is they have more electrons that are able to jump in different energy level gaps. Now, as it so happens, we have an equation that can help us understand the type of light that is given off from these energy level changes based on how much energy is involved. So the equation is E is equal to the frequency of a wave multiplied by something called Planck's constant. So this is just really a three-part equation where E is going to be the energy released when an electron jumps down from one energy level to another. So if we look at the gap between, say, the third energy level and the second energy level, the amount of energy that it takes to get an electron up to that energy level is going to be the same amount that is released when the electron jumps back down. So those energy level changes are the same. Now, where does that energy go? It goes into the type of light that's being released. It produces a light wave or a photon. So the type of light that comes out, of course, is going to depend on how much energy there is, and we can calculate that by this equation. And we'll do a couple problems here just to see how this works. So frequency is something we've talked about before when we talked about the properties of waves, and we can relate frequency and wavelength, and we'll have to do that here in just a little bit. But h is just a number. It's called Planck's constant, but it's a very small number. Planck's constant is 6.63 e to the negative 34th, and the units are joules times seconds. And the unit part we don't have to worry about too much. They're really just the joules times seconds is there so that the units work out correctly for the frequency and for the energy. So that's just a number. Okay, we put that number into each equation because it is a constant. So that's another good thing that you could put into your calculator. So we talked about how to store Avogadro's number for m in your calculator so that you didn't have to type that out all the time. This is another good one because you're going to use it, anytime you do this equation, you're going to use Planck's constant. So h would be the obvious choice. You can just store that in your calculator so you can multiply it or divide it easily. So let's do an example problem. Let's do that. So let's say the energy level jump from an electron jumping from the second energy level down to the first energy level, we know is equivalent to about 8.94 e to the negative 17 joules. What we want to do is figure out what kind of light is going to be produced when that electron jumps down from the second energy level to the first energy level. So the first thing we need to do is to relate this to the frequency of light using that equation we just learned. So this is going to be the energy. So we put in 8.94 e to the negative 17. We're going to leave units off for now just to do the math. And that we know is equal to the frequency multiplied by Planck's constant. So you can just use h on your calculator, but I'm going to put it in here. 6.63 e to the negative 34. So this is a pretty simple equation to use. All we have to do is divide. So we take 8.94 e to the negative 17th divided by 6.63 e to the negative 34th. And we should get a frequency of about 1.35 e to the 17th. Okay, and if you remember, when we're talking about frequency, that units for that is going to be in hertz. So just a reminder, that means that when this wave comes out, if you measured a certain place, 1.35 times 10 to the 17th waves would go by that spot every second. Remember, the whole point is because those are moving very quickly at the speed of light. Now, what we want to do is relate this to an actual wave. So we can then take our other light equation, where the speed of light is equal to the wavelength times the frequency, and we can put this number here in for frequency. Of course, the speed of light is always the same, and what we can do is calculate the wavelength. So the speed of light we'll put in as 3.00 times 10 to the 8th is equal to wavelength times 1.35 e to the 17th. And then in this case, we're going to divide again. It's another three-part equation. And we get a wavelength of 2.22 e to the negative 9th meters. And it just so happens that that's going to be somewhere in the top of the UV spectrum. So that would be a type of ultraviolet light given off by this electron jumping from the second energy level down to the first energy level. Okay, so this is a typical type of equation that you may see. Another typical type problem would be to measure the wavelength of light. So measure the type of light that is given off by an electron that's jumping energy levels, and then relate that back and see what that energy is. What is the actual energy jump from whatever to whatever level when that electron jumps down? So let's try a problem like that. So here we can use a fairly simple example. I've got a green laser, and on the laser it says it shoots light at a wavelength of 532 nanometers. Now, I'm not going to make you go through all the conversions for that, although you should be able to do that. But if we convert 532 nanometers into meters, we get 5.32 e to the negative 7th lasers. So that light is being given off when that laser shoots across the room. And it's given off because there's energy level transitions of the electrons in the laser. What we want to know is, what is that energy? How much energy does it take to jump an electron up to that higher energy level, and how much energy is released when that electron comes back down? I'm going to put 5 minutes up on the board. That should be enough time for you to give this a try, and then I'll go through how to do it, and you can check your answer.
Okay, so in this case, we're basically just going to work backwards from where we did. We want to eventually use this equation. We want to figure out what the energy is, so that has to be this equation right here. The problem is we know h, that's Planck's constant, but we don't know what the frequency is. So before we can use this equation, we first have to use our speed of light equation to calculate what the frequency is. Then we can put that frequency into the other equation. So here again, we would put 3 e to the 8th equals frequency times 5.32 e to the negative 7th. In this case, we will divide. In this equation, because the speed of light is constant, we always end up dividing the speed of light by something. And we get a frequency of 5.64 e to the 14th hertz. Now this frequency we can then take over and put into this equation right here, and we're going to end up finding energy. We basically end up multiplying that number times Planck's constant. So we'll multiply that by 6.63 e to the negative 34th, and the energy here should be 3.74 e to the negative 19 joules. So that's the energy level gap between that transitional energy level where the electron is jumping to give off that green light.
Homework for Friday is worksheet 3.5. So do those problems, and on Friday we'll go over them.